So we're going to start with valence electrons, Lewis dot, and ions. All right. So what are valence electrons?
Outermost shell.
Yes, the electrons in the outermost shell or in the highest energy level. All right. And so elements with the same number of valence electrons are going to act the same chemically. All right, because they have the same number of valence electrons. Valence electrons determines how they bond, what they bond with, etc. All right, determines their chemical properties. So, what we know about valence electrons is that the group number represents the number of valence electrons. All right, for our A group. So group 1, 2, 13, 14, 15, 16, 17, and 18. What is the max amount of valence electrons I can have? 8. There we go. Good job. Octet rule, yes. So group 1 has how many?
1.
Group 2?
2.
Group 13. 3, 14. 15. 16. 17. And 18. 8. But what's our exception here? What about helium? Helium only has 2 electrons. So why is helium in group 18 with our noble gases? So noble gases have 8 valence electrons. What's special about 8?
Because you can't go higher, so then it goes to other clumps.
Right, so 8 means it's full, right? Remember we compared them to noble kings, noble gases, and we said the noble kings have everything they want. They're full and content. They couldn't want anything else because they have everything. All right? They don't want to bond with anything, just like the kings didn't want to mix amongst the other people. They're fine all by themselves, right? But remember our Bohr diagram, our Bohr model. All right? So if we look at neon, how many is on the first shell? 2, and then the next shell has, again, what's a full shell? 8. All right, so here's a full shell of 8. That's neon right here. All right, so what is special about helium?
Oh, it can't go higher than that because it's full of 2.
Yes, it also has a full shell, but its full shell is just a little bit smaller, right? It fills the first shell. Everything else fills that outer shell. All right, so then we looked at the D block, which typically has 2, but it can vary, and then our lanthanides and actinides, which also typically have 2. So here you see that again, and those numbers representing it. And so here you see your A block elements, 1, 2, 3, 4, 5, 6, 7, and 8. That tells you the number of valence electrons. Notice that's group 13, 14. That's the second number in the group number. All right? So then we illustrated our valence electrons as dots using the Lewis dot symbol. What is the max amount of dots you could have around your symbol? 8. Yes, all right? So I don't want to see 21 dots piled around an element because the max we can have is 8. We're talking about valence electrons here, not total electrons. All right, so in our valence, or in our Lewis dot symbols, the first thing we would do is write our chemical symbol, determine the number of valence electrons, and then put a dot on each side for each electron. When do we get to double up? Once you fill up all 4. Remember, they're socially distanced electrons, all right? They all want a seat to themselves until we run out of room and we have to double them up. So let's look at some examples. If you didn't fill this out in your table, do it along with me. All right, so Ga, gallium, how many valence electrons? 3, good job. It is in group 13, so it has 3. All right, xenon, group 18, it has 8. Calcium is in group 2, so it has 2. Nitrogen, group 15, has 5. Iodine, group 17, 7, good job. And aluminum, group 13, has 3. All right, so you're looking at the group numbers with your columns. All right, so let's look at our Lewis dot symbols. For gallium, I've got Ga here in the middle, and then 1, 2, 3. It does not matter where those dots are, as long as they are on separate sides. All right, this bottom one could be on the left, the top one could be on the bottom. All right, it does not matter as long as you have them all on a side to themselves. Then we had xenon, Xe. 1, 2, 3, 4. They're all full. Now what do? Yes, good job. Fill them all the way up so we get to 8. Calcium, Ca. 1, 2. You can have it on the top and the side, the top and the bottom, the two sides, wherever, as long as they are not side by side. Nitrogen, 5. 1, 2, 3, 4, 5. Doesn't matter which ones you double up, but you'll notice as we go through this and start building Lewis dot structures, that it'll be easier to put them in different locations. All right, we'll see that more in next class. Iodine has 7. So 1, 2, 3, 4, 5, 6, 7. Bless you. And then lastly, aluminum has 3. Al. 1, 2, 3. Notice aluminum and gallium both have 3. They're in different spots. It doesn't matter where we put them. All right. Questions on Lewis dot? That should be a review for you. Are we good? All right. So then what does our octet rule mean for our valence electrons? Our octet rule tells us that atoms tend to gain, lose, or share one or more of their valence electrons in order to achieve that filled outer shell. All right, so they gain or lose in our ionic bonds, or they share them in the covalent bonds in order to have a full shell. All right, how many valence electrons do those noble gases have? 8. Well, everybody wants to be like our noble kings, right? They all want to have 8. So the only exception is the first 5 elements. Why? Well, first off, let's think about why was 8 important? Because 8 is a what?
Oh, filled outer shell.
Filled outer shell, yes. All right, well, the first shell only holds how many? 2. So hydrogen just needs to gain 1 more. Is this shell full?
Yes, because it's 2.
Yes, because it's that inner shell of 2. Helium has 2. Is it full?
Oh, yes.
The inner shell, yes. Lithium, all right, it has 1 valence electron. Does it want to try and gain 7 more electrons? Or could it just lose this 1? Lose that 1, and what happens? That shell disappears, and I'm back at a full shell. Same thing with beryllium. It's going to lose these 2 valence electrons. That shell is going to disappear. All right? And I now have a full shell. And lastly, element number 5, boron. All right, I lose those 3 because it's easier to lose 3 than it is to gain 5. And I get back to that full shell. All right, so that is why your first 5 elements are an exception, because it's easier for them to drop back to that 2 on the first shell than it is to get all the way up to 8. All right, so when they gain and lose, they become ions. All right, we had 2 types of ions. Cations are positively charged. If they're positive, what happened to our electrons? We lost them. All right, so we lose electrons and become positive. Think here's the plus and cations. All right, so it reminds you that it's positive. Or cats have pos, like positive. All right. And then if we go the other way and we gain electrons, I've gained negativity, right? Because electrons are negative. And if I gain negativity, I become negative. All right, which is a anion. Think anion, antagonist. Antagonist is the bad guy or the negative guy, right? So gaining electrons makes me an anion.
Yay.
All right, so write the symbol of the ion formed when a sulfur atom gains 2 electrons. Sulfur, I'm gaining electrons. I'm gaining electrons, I'm becoming. Gaining negativity, so I'm now negative. And how many did I gain?
-2.
2. All right, and aluminum loses 3 electrons.
3.
Positive, because I'm losing negativity, I'm now positive. All right, let's look at the following. How many electrons are lost or gained? All right, so barium 2+. If I'm now positive, what did I do to the negativity in my life?
-2.
I lost it. All right, think of it in terms of lose and gain. All right, arsenic, I've got 3. I gained 3, gaining and losing. All right, and then copper. All right, 2+, how did I get positive? I lost 2. All right, questions? Those of you online, are we good? All right, awesome. So to tie that together, groups 1 through 3 are losers because it's easier for those to get back to 0 than it is to go all the way to 8. So they want to get rid of those valence electrons so that they drop back to their last full shell. All right, and when they drop back to that last full shell, they end up with a positive charge because they lost negativity. All right, group 4 will lose or gain depending on what it's combining with, whatever it's forming a bond with. And then groups 5 through 7, it's easier for those to get to 8, so they're going to gain electrons, which means they're gaining negativity. They're going to be negative, all right, and they're going to get to that full outer shell. So here we see that just kind of summed up. You see your positive 1, 2, 3, and then plus or minus 4, and then 3, 2, 1. And group 18 doesn't want to do either, so that's why you see 0. It's neutral. All right, so tying it together, we know that our metals are on the left side of the periodic table, and they lose electrons. So when they lose the negativity, they become positive. All right, which means they form cations. Non-metals gain electrons. They gain negativity. That means they're negative. So look, non-positive. Little reminder key. Non-metals are non-positive. So in your sheets, you should see this. Let's take a second and practice our valence electrons and their charges. All right, gallium. Again, we have how many valence electrons with gallium? 3, because it's in what group? Group 13, yes. Is it easier for it to get back to 0 or go to 8?
Get to 0.
Go to 0. So Willie Kate, what do I do to get to 0? Lose 3. All right, when I lose that negativity, I become positive by however many I lost, which was 3. And positive is a cation because it is positive. All right, sulfur, what group number is it in?
2, 12, wait, no, 16.
16, yes. So how many valence electrons? 6. Is it easier to get to 8 or to 0? 8, so what do I need to do in order to get there? Gain 2. All right, which makes me negative by 2 because I gained negativity. When I gain negativity, I become negative like a anion. We're coming to it. Rubidium. It's in group 1, so it only has 1. All right. Yes, it wants to lose to get to 0, which means I have a positive 1 charge, which is a cation, because that T looks like a plus. All right, and then she just asked, what happens if it has 8? Well, let's look at argon. Group 18, so it has 8. Gain or lose? Neither. So Na. Neither, Na, you can leave a blank, whatever. All right, is it gonna have a charge? No. Doesn't want to get rid of anything it has, right? And cation or anion?
Neutral.
Na, yes, it is neutral. And lastly, we had nitrogen. Group 15, so it has how many valence electrons? 5. Gain or lose? Gain. How many does it need to gain? 3. And therefore my charge is going to be -3. Yep, and good job. I have a anion. Last bit. All right, ionic bonds. Ionic bonds result from electrical attraction between cations and anions. All right, so what happens is your cation transfers that electron over here to your anion. All right, and now sodium becomes what? +1. And chlorine becomes -1. Well, we know that opposites do what?
Sure.
Attract. So here's our opposite charges. They attract. Think of them as like magnets, right? They're still two separate entities, but they're attracted to each other, which holds them together. This right here is table salt. This is what you eat at dinner. All right? And they're attracted to each other. That's what holds the sodium and the chlorine together, is they act as, think of them as two little magnets, all right? And so that transfer of electrons gives them a charge, all right? And that charge is what attracts it. And so in doing that, we see that ionic bonds are made up of metal cations, which contribute the positive charge, and non-metal anions, which contribute the negative charge. So even though they're composed of ions, meaning one of them's positive, so one of them's negative, all together they are what? Electrically neutral. Good job. All right, that means that whatever positive charge I have to equal it out with negative charge. All right, so total positive must equal total negative. So here we see that with lithium, all right, it wants to get rid of this electron. So it transfers it over here to fluorine. Fluorine is now negative. Lithium's positive, and they have happy faces because now they're content. They both have a full outer shell. And so for every one lithium, I need one fluorine, so LiF. But then what if they're not the same charges? So here I see magnesium, and magnesium has 2 valence electrons, and it wants to give those away. Well, chlorine can only take one of those, right? So what do I need? Chlorine can only take 1, but magnesium wants to get rid of 2.
Another one.
Yes, I need another chlorine. Good job. All right, and so I have 1 magnesium, 2 chlorine. That's why your swap, drop, and chop works. Mg1Cl2. All right, so then you see your magnesium chloride. That is your ionic bonding.